All right, last time we were talking about the hydride delivery reagents, sodium borohydride, which is reactive enough to react with aldehydes and ketones, but not with esters. That makes sense because aldehydes and ketones are more reactive than esters. Then we introduced a superpowered reagent, lithium aluminum hydride, more reactive than sodium borohydride because the electronegativity difference between aluminum and hydrogen is bigger. And LAH, lithium aluminum hydride, you'll see people abbreviate this as LA. In any case, that's good enough for reductions with esters as well. So things that are as reactive as aldehydes and ketones, no problem. Esters, no problem either. And I showed you how that works. You get one hydride delivered to the carbonyl carbon. You get a tetrahedral intermediate. Best leaving group relative to the negatively charged oxygen leaves. That gets you to the aldehyde. But what happens is that the aldehyde is more reactive than the ester starting material, so you can't stop there. A second equivalent of hydride gets delivered to give you this tetrahedral intermediate where you have no good leaving group relative to the negatively charged oxygen. There you stop until aqueous workup, and that gets you to your primary alcohol product. I told you this reaction series wasn't worth memorizing because if you know carbonyl chemistry, you can figure out the mechanism. The thing you would need to memorize is that lithium aluminum hydride simply can't stop at the aldehyde. And at the end of class, I told you about dibol H, the reagent that can stop at the aldehyde. You can't see my little stick figure Gandalf saying, "You shall not pass there." In general, Lord of the Rings references don't do well in your demographic, as well for your demographic as do maybe Star Wars references. So I don't know. We'll try to. I can do some Lord of the Rings references, but I'm not as strong on them. Anyway, dibol can stop at the aldehyde, and the way it does this is really interesting. Your text doesn't show you this, so I wanted to just take a minute and show you. One of the things you might notice is that unlike lithium aluminum hydride, dibol hydride doesn't have a negatively charged aluminum. So you might think, how is that thing reactive at all? And the answer is it's not until it sees the ester. So if you remember your periodic table, that's the big disadvantage of this room. We don't have one, so you have to see it in your mind palace. Aluminum is from the same column as boron. So aluminum with three things attached to it has an empty p orbital on it. And so the thing that happens first is a Lewis acid, Lewis base, nucleophile attacks electrophile reaction. Carbonyl oxygen attacks the aluminum. That creates a new oxygen-aluminum bond. And that conveniently gives you a negative formal charge on the aluminum and a positive formal charge on the ester. That does two things. That first turns on the reactivity of the aluminum. Second, the positive formal charge on the carbonyl carbon turns on the reactivity of the ester. So these two molecules, when they find each other, become much more reactive. And the aluminum hands off the hydride directly. I guess my drawing is not that good, but whatever. The aluminum hands off the hydride directly to the carbonyl carbon. It's an intramolecular reaction at this point, and that intramolecular reaction is relatively fast. And that gets you to the following tetrahedral intermediate. Too many carbons on that aluminum. And it turns out that this intermediate is stable. Notice that the oxygen, normally we've dealt with tetrahedral intermediates shown up here where you've got a negatively charged oxygen and that can kick off the methoxy leaving group. Here the oxygen's not really negatively charged. So this intermediate is stable. Nothing else happens until aqueous workup. When aqueous workup happens, I won't show you this. I could, but it's really not worth our time. Basically what happens is water attacks the now empty p orbital on the aluminum to create a negatively charged aluminum species, which just leaves and releases the negatively charged oxygen. So in the presence of water, the aluminum falls off this intermediate. You get back to your regular everyday tetrahedral intermediate, where you have a negatively charged oxygen that's a good enough internal kicker-offer to kick off the methoxy leaving group. And then the reaction just proceeds as expected. Methoxy leaves and your aldehyde is the product. The trick is, by this point, the aluminum reagent is consumed. There's nothing else ready to go. There's no other hydrides to be delivered. And so because of that, you can stop at the aldehyde because you've already consumed whatever hydride delivery reagent you have. So Dibol is able to take, and maybe I'll just summarize the reaction mechanism with just drawing it out here, is able to take an ester and stop at the aldehyde, whereas lithium aluminum hydride, as you've seen, cannot stop at the aldehyde. Okay. Often people do not show aqueous workup steps above or below the arrow. When you're in the lab, you sort of just know you have to do that. Your text will tend to specify this by putting like step 1, Dibol hydride, or step 1, lithium aluminum hydride, step 2, water. Understand that when they do that after a lithium aluminum hydride or a Dibol reduction step, they just mean aqueous workup. There's nothing more complicated than that the water's supposed to do. Okay, so that's not in your text. Your text didn't show you that mechanism. If you want to memorize that Dibol can stop at the aldehyde, that's fine, but now you know how it works. Questions about that? Yes?
Does the Dibol ever react with ketones?
Can the Dibol react with ketones? Good question, and I don't know. Some of my colleagues that are a little bit more experienced with synthesis would know that. Your text doesn't give you any examples of that, so yeah. What else? Yeah?
Can Dibol react with acid chlorides?
Can Dibol react with acid chlorides? Yes, you can use it interchangeably. So there's a couple of reagents that are introduced as being able to stop at the aldehyde. I've shown you Dibol, and your text basically says you can use Dibol for acid chlorides as well. So same sort of deal. Dibol is able to stop at the aldehyde with acid chlorides, whereas lithium aluminum hydride is not. I will just, hold on, sorry, catching up to myself. Others? Saw another hand, no. I got to scan a wider field of vision here. This is a big test on my peripheral. Yeah?
What's the pKa on the methoxide?
pKa on the leaving group, the methoxy leaving group, what you want is the pKa of its conjugate acid, which is methanol, and that is 16. Yeah. Okay, the one other thing that's introduced as being able to stop at the aldehyde, this sort of alternative to Dibol, I'm going to list here, and then we're not going to say very much about it, mostly because your text doesn't. This is basically, I would say, an attenuated version of lithium aluminum hydride. By attenuated, I mean its reactivity is lower. So compared to lithium aluminum hydride, and I'm not even sure how to pronounce this, I would call this lithium tris-tert butoxy aluminum hydride, which I'm sure you don't want to say, and I don't really want to say, and your text abbreviates it even worse than I'm about to. Why might this be able to stop at the aldehyde? Your text gives one reason, and that is sterics. It says somehow the bulky tert-butyl groups help with the reactivity, turning it down relative to lithium aluminum hydride. I can think of another reason, and that is the presence of those electronegative oxygen atoms, which should pull electron density away from the hydride, making this reagent less nucleophilic than lithium aluminum hydride. That being said, you can use this on esters and aldehydes I didn't mean esters and aldehydes, I meant acid chlorides. So use this on esters and acid chlorides to stop at the aldehyde. Your text introduces them in the same section it tends to use. If you're following through the examples with a fine-tooth comb, it only ever really uses Dibol with esters, and it only really ever uses this reagent with acid chlorides, though it never tells you that that's what you're supposed to do. So you can feel free to use these two reagents interchangeably. in terms of why Dibol works. I've shown you that. I'm not really going to, aside from these explanations, which are mostly hand-wavy, not going to get into the explanation of why this one works. But your text wants you to be able to use both of them. All right, other questions? Yeah.
I'm assuming that one has an aqueous work of this one.
Yes. Yeah, usually after all of these steps where you're using heavily nucleophilic reagents, where you're generating a negatively charged tetrahedral intermediate, usually there's aqueous workup, yeah. I skipped it above because I was lazy. All right, what else? Okay, let's talk nature. How does nature do reductions? Obviously, if you've got lithium aluminum hydride, which can cause a fire in water, that's why nature doesn't use that, right? So nature has another reagent, and you've read about this in your text. We don't want to spend too much time on it, but this is called nicotinamide adenine dinucleotide. In its reduced form, it's called NADH. I'll trust you to look up that and understand what NADH means. I'll show you part of the structure. The structure that's relevant for the reduction reaction is as follows: a 6-membered ring containing a nitrogen with an amide group coming off the nitrogen, 2 double bonds here, and 2 hydrogens here. Then the nitrogen is bonded to something else, which we're going to abbreviate with R. Lone pair on the nitrogen is important. This portion of the molecule is called nicotinamide, but it's also called niacin, which is vitamin B. It's either 6 or 3. Anybody know? 3? Some of you say 3, some of you say 6. So truth is what the most people vote for. Isn't that right? Is that how we define truth? I don't know. We'll look it up. Somebody Google it and you can correct me. Okay, fine. I'll Google it. Niacin. Wikipedia. B3. Okay. So when you eat something with vitamin B3, it's got this portion is called niacin. It can be in a carboxylic acid or amide format, but in any case, you need this to do reduction reactions, and its oxidized form you need to do oxidation reactions. The hydride that gets delivered is right here. So as an example, under sort of anaerobic conditions, as you're metabolizing glucose, the endpoint of the glycolysis pathway is a molecule that's called pyruvate. And normally that gets shunted to the citric acid cycle via a pyruvate dehydrogenase complex. And then acetyl-CoA goes to the mitochondria, and the citric acid cycle turns and drives the proton gradient, and you get ATP. But if you're under sort of anaerobic respiration conditions, pyruvate starts to build up, and you need something to do with it. And so one of the things you can do is you can take NADH, and you can reduce pyruvate to a molecule that's called lactate. So I'm just going to draw the structure of lactate for you. It's a carboxylate with, on the alpha carbon, an OH group. And now you can start to see the differences, right? Here is the oxygen on the ketone. Here, that same oxygen is an alcohol. What happened? We delivered a hydride. We did a reduction of the ketone to the alcohol. And the way this happens is direct handoff of a hydride from NADH to lactate, to the ketone carbon of pyruvate. H minus, it's exactly like lithium aluminum hydride reduction. H minus never leaves and is on its own. It's just handed off directly like a baton in a relay. You can draw the arrows for this reaction simply by showing the hydride coming off NADH attacking the ketone carbonyl to get, yes, a tetrahedral intermediate, which would look like this, where here is the hydrogen that got added. And then that negatively charged oxygen would get protonated by something, either water or perhaps an acidic group in the enzyme active site to give you the lactate product. I will also draw for you real briefly what NADH becomes after it loses the hydride. And it becomes something that we call NAD+. So I'll draw that for you here. We're going to draw everything about NADH, only the hydride is going to be missing. If the hydride left, that would leave a positive formal charge on that carbon, which you might think, hey, that's terrible. However, that positive formal charge is delocalized by resonance. You should be able to see without too much trouble how I could draw a resonance structure for that nicotinamide portion of the NAD+ molecule that would show that that positive charge is delocalized by resonance. It turns out we haven't learned about this yet. We're going to get to it in a later chapter. But this cation, NAD+, is stabilized by something that I want you to write down and then forget for a while, and that's called aromaticity. Aromaticity is a special property of cyclic conjugated systems if they have the right number of electrons. This one happens to. 6 electrons is a magic number for reasons we'll talk about later. But one of the things that pays for the loss of the hydride from NADH is the fact that the resulting NAD+ is what we're going to call aromatic. We'll come back to that later. There are other reagents that biology uses to do reduction reactions. This is just one of them, but it's one of the most important. Also, NAD+ can do oxidation reactions. So for some reactions, and when we get to metabolism, you will see that some substrate molecules will actually lose hydrides and they will get delivered to that positively charged carbon. All right, anything more we need to say about that? Questions? All right, yeah.
Is this enantiomeric selective?
Enantioselective, good question. The answer is yes, because this molecule, as you've noticed, we get this particular stereochemistry at the carbon where the reduction reaction happens. So yes, that means the hydride is preferentially delivered from, as we've drawn pyruvate, from the top face of pyruvate. Now normally, if you're doing a reaction and the starting material is not chiral and the reagents are not chiral, you can't have a reaction that is, what you said, Miriam, enantioselective. The thing that makes this reaction enantioselective is that the enzyme that catalyzes it, called lactate dehydrogenase, is chiral. And so the chiral enzyme controls which face of the ketone is next to NADH and therefore which face accepts the hydride. That's an important point because the reagents that we just barely talked about are not enantioselective. So let me just show you that in contrast. Probably should have done it earlier, but it's a fair point that we ought to just illustrate now. Let's draw not lactate, but just some ketone. Here is a ketone, and for a reagent, I'm going to choose lithium aluminum hydride, though I could have chosen sodium borohydride. Remember, I'll draw the tetrahedral intermediate. The starting material is not chiral. The tetrahedral intermediate is. Here's the hydride from lithium aluminum hydride that got delivered. And it must have been delivered from either side. That means we get both possible stereochemical configurations. So for completeness, if I wanted to show the product here, I could show both enantiomers. I could draw them out explicitly like this, one in which the hydride was delivered from the top face, one in which the hydride was delivered from the bottom face. Alternatively, it is perfectly permissible when I mean that this stereocenter has both possible configurations to just draw it with lines. When I draw a stereocenter that way, I'm not communicating that all the lines that are lines are in the plane of the page. You sort of have to know what you're doing when interpreting, easy for me to say. OChem structures. I have to know that that carbon's sp3 hybridized tetrahedral, and that because I haven't shown dashes or wedges, I mean both configurations are present. Both enantiomers are present in a 1-to-1 ratio. An alternative to even that is to draw only one enantiomer and then add a little plus or minus in parentheses, which similarly communicates that I have both stereochemical configurations. That should be a review. You probably learned that in 351, but that's how we'll handle stereochemistry in cases like this. But notice this not chiral reagent and this not chiral starting material lead to products with such that the reaction is not enantioselective. We get a racemic mixture of enantiomers. Okay? All right, others? So it sort of completes the hydride nucleophiles adding to carbonyls. We're going to spend the rest of our time in this chapter on carbon-based nucleophiles for carbonyls. So I'm going to introduce 3 different kinds of carbon nucleophiles. And these are basically, you can think of them as carbanions. Now, just something about a carbanion, you would expect something like CH3 minus to be a really, 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 really strong base and a really, really, really good nucleophile. And the reason you expect that is because its conjugate acid, if you remember from 351, has a pKa of somewhere in the 40s or 50s. It's astronomically high, okay? Because of that, because it's actually so hard to get that proton to come off in the first place, the way we generate these nucleophiles and the way we use them is not really in their pure anion form. So let me show you a reaction that generates something that you can use as though it were a carbanion. Here is an alkyl halide. This is just methyl bromide. If I use lithium metal, so when chemists want to indicate that they're using a metal, sometimes they'll write the metal and they'll write a little 0 subscript to indicate this is lithium metal in its 0 oxidation state. In the presence of this metal, there's a reaction that goes on between the metal and the alkyl bromide. I won't show you the details of that reaction. It's known. If you want to go look it up, you can. Just Google halogen metal exchange. It's a little bit weird, and it involves single electron transfer, which if you're interested in that, more power to you. But what this actually does is it creates a new bond between carbon and lithium, and then Br minus is the leaving group. And the weird thing about this carbon-lithium bond is it's tempting to think about this molecule as though it were simply CH3 minus and lithium as the counter ion. But there's evidence for a fair amount of covalent character to that bond. And we called this reagent an organolithium reagent. And it's basically a carbon nucleophile. For all intents and purposes, you can think of it as though it's simply the carbanion, but you always sort of have to keep in the back of your mind that lithium's around there doing stuff. The chemistry of organolithium reagents is really complicated, and it's probably beyond the scope of an undergraduate class. So we won't say more about that. However, your text in synthesis problems will expect you to start from an alkyl halide and generate an organolithium reagent. And you're going to forget how to do it and need to go back and look it up, and you're going to think, did we ever learn how to do that? And then you'll think, oh yeah, there was that one time for 2 minutes in class we talked about it. This is how you do it, okay? And you can use this as a carbon-based nucleophile to do addition reactions and substitution reactions to carbonyls. So let me give you some examples of reactions you can do with organolithium reagents. What I'm going to show you should not be a surprise because it's going to mirror what you've already done with lithium aluminum hydride and the hydride delivery reagents. So let's use methyl lithium as our nucleophile. Remember, you're going to think of this as basically a carbon nucleophile delivery reagent. The carbon will take the electrons from the carbon lithium bond and attack the pi star, breaking the carbon oxygen pi bond and creating a tetrahedral intermediate. We think that's reasonable because a carbanion-like nucleophile is way more reactive than the negatively charged oxygen in the tetrahedral intermediate. So seems totally reasonable to make that tetrahedral intermediate. At that stage, you ask the question, all right, here's the kicker-offer group, and which is the best leaving group relative to the negatively charged oxygen? It's the chloro group, which is a way better leaving group than a negatively charged carbon. So what happens next is electrons kick down, the chloro leaving group leaves, and then you just made a ketone. Now, we kind of have a problem in that a ketone is still very reactive. Remember that acid chlorides come at the top of our list of reactive carbonyl molecules, but so do ketones. And so you would be right to worry about, does methyl lithium attack again? And in fact, stopping methyl lithium from attacking the ketone is something that people have not been very successful at doing. So in practice, when people are doing this reaction, they add enough methyl lithium so that you can deliver the first equivalent to convert the acid chloride into the ketone, and then we'll do a second round again with the second equivalent to generate this tetrahedral intermediate. At this point, we've got two equivalents of CH3 that have been added to our molecule. By analogy, if you want to scroll back up in your notes, at this point with the organolithium reagent, we are exactly where we were before when we were using lithium aluminum hydride on the ester. That is, we had a tetrahedral intermediate where we had added two hydrides. And at that point, there were no good leaving groups. Similarly, when we're using the organolithium reagent, we get to this point where we have a tetrahedral intermediate that's got no good leaving groups, and so there we stop until aqueous workup, which will often be included through this kind of an arrow. I'm sorry, for this sort of reagent over the arrow. I guess I've duplicated myself, so whatever. Oh, now, great, now I erased it all. So. That will protonate the negatively charged oxygen, and the product of this reaction, starting with an acid chloride and using an organolithium reagent, is a tertiary alcohol, where two of the same thing are attached to the carbon of the tertiary alcohol. That's a structural pattern that's good to recognize. When you see a tertiary alcohol and you notice that two of the groups on that tertiary carbon are the same, you should be thinking in your head, oh, I could have, or the synthetic chemist would be thinking in their head, and if you want to do well on some exam problems, that probably needs to be you. Should be thinking in your head, I could have made that by using an organolithium reagent on something like an acid chloride or an ester. We could swap out that acid chloride for an ester and get exactly the same thing. They react in analogous ways. So if I use this organolithium reagent followed by aqueous workup, I would, from the ester, likewise get the same tertiary alcohol product. And the take-home message here is that organolithiums, like lithium aluminum hydride, organolithiums can't stop after just one addition. Right, so the organolithium reagent will not stop at the ketone, it's going to proceed to the tertiary alcohol. So that's one way we can use these carbanion-like nucleophiles to do, in this case, the first round was a substitution reaction via addition and then elimination, but then we get a second round of addition and there we stop because we don't have a good leaving group. Questions about that? Yeah.
So can you also make an organolithium like a more flat carbon chain than
Can you make an organolithium with anything other than just methane? Yes. So any alkyl halide or aryl halide that you can make is you can do the corresponding organolithium reagent. So you'll see a lot of examples of organolithium reagents in your text. I'll just draw a few: phenolithium, butyllithium, basically anything you can think of. Yeah. Okay, others? So I told you I'd introduce another. But before I do that, let's just predict products. At this point, we're mixing and matching carbonyl reactivity with various reagents. So what if instead of using acid chloride or an ester, what if instead we used an aldehyde? Go ahead and predict the product for that reaction. You got 30 seconds. Go. You guys know the Jeopardy show? I did this once in class and it totally stressed out people. They were like, all right, are you done? Take maybe another 15 seconds. Okay, what's your product? Tell the Apple Pencil what to do. Okay, what else you got? That's it? Wrong. What should be on the oxygen? An H, it's an alcohol, and then what? Add a phenyl group, which I'll abbreviate with a pH. Good. If you drew this, you're fine. If you drew it this way, you're fine with the plus or minus. If you drew both enantiomers, you're fine. The point is that you deliver one equivalent of the reagent, then when you draw the tetrahedral intermediate, you ask what happens next. Is there a good leaving group? The answer is no. So there you stop until aqueous workup. Okay. Questions? So there's another kind of reagent that works basically the same way as the organolithiums. Your text probably, if it wanted to just be bare bones, would give you one, but not both of these. However, this second class of reagents that are called Grignard reagents are quite famous. And if you take the undergraduate organic lab class 353 at BYU, you will use a Grignard reagent. Grignard reagents are formed in basically the same way as organolithiums, only they use magnesium as the metal instead of lithium. And magnesium, if you looked in the periodic table, comes from the second column. In its ionic form, it has a +2 charge. So the Grignard reagent actually looks like this. You have a covalent bond between carbon and magnesium. And then the magnesium has also a Br- counter ion. And this could actually be chloro. There are chloro versions of Grignard reagents. There are magnesium versions of Grignard reagents. It's fine if you want to think of this as the carbon ion, a magnesium 2+ ion, and then a Br- ion. Though there is evidence that there's covalent character to those bonds. Even though I've drawn it that way in the text, most often it will be drawn with just MgBr together. All right? We won't dissect the structure of the Grignard reagent in any more detail than that. Again, the reactive portion is going to be here in this bond between carbon and magnesium. As with the organolithium reagents, you can't stop at the ketone. So just to do a quick example, if you use this ethyl Grignard reagent followed by aqueous workup, you would expect to get the tertiary alcohol where 2 ethyl groups got added. There would have been a first one be added to give a ketone intermediate, and then the second added to give you the tertiary alcohol, analogous to what we did previously with the organolithium reagents. So you can use the Grignard reagents basically interchangeably. I'm not sure whether you drop the E after interchange if you're making it interchangeable. I also don't care, so feel free to email me and I will delete it about that particular issue. You can use them interchangeably with organolithium reagents. As with the organolithium reagents, we can't stop at the ketone. All right, so you know what's coming next now. Organic chemists are never content with limitations. Is there a reagent we could use with the acid chloride to stop at the ketone? And the answer is yes. So we're going to introduce our third and final carbanion-like reagent, and this is called the organocuprate, and or just sort of cuprate for short. It's going to involve copper. The text is not telling you a lot. Cuprate chemistry is actually really detailed, and there's a lot we could get into. It involves some things about transition metal chemistry and how you can have more than 8 electrons around a transition metal. We're basically going to have to memorize what cuprates do because we're not going to look at their reactivity in a lot of detail. I'll show you how you make these because your text will expect you to be able to do this. You start out with, to solve some synthesis problems, you start out with the alkyl halide, and first you convert the alkyl halide into the corresponding organolithium reagent, so ethyl bromide to ethyl lithium. Then if you add copper iodide, this is copper in the +1 oxidation state, so that's just copper plus. The reagent that forms is as follows: a copper bonded to 2 of the R groups. So obviously you would need 2 equivalents, or for every mole of copper iodide, you need 2 moles of the ethyl lithium. That creates this copper reagent that's called a cuprate because it has a negative charge on the copper. The counter ion is just lithium. Okay? People will abbreviate this as R2CuLi. That's a cuprate. And again, its chemistry is way more complicated than I'm giving you here. It's more complicated than I understand. But you can think of this as basically, again, a carbanion delivery reagent. But it's going to be different and have unique reactivity in a couple of ways. The first way falls directly in line with what we just talked about. The first unique reactivity is cuprates can stop at the ketone. And your text delivers this as a fact without further explanation, and we're just going to go with that. So this is going to be something that you memorize. A more detailed explanation is beyond the scope of what's this class, and it's also not even in my brain. I care about other things. You have to stop caring at some point, right? At least I can. I'm the professor. What I care about doesn't. Anyway, you have to care about everything that I care about. You're not laughing, neither should you. It's kind of a pain situation to be in. Let's show you how cuprates can stop at the ketone. So here is an acid chloride. Your text will show you a cuprate reagent. Let's use that diethyl cuprate that we just made above. You can remember the lithium counter ion or forget about it. What happens is, again, we'll use the bond between carbon and the metal to deliver a carbanion to the carbonyl carbon of our acid chloride to give us our tetrahedral intermediate. Again, we will ask the question, do we have a good leaving group relative to the negatively charged oxygen? And if so, which is the best one? Here it's the chloro, and so chloro gets kicked off and leaves. But then here's our product, and it's a ketone where we have added one and only one of the groups that are on the cuprate. There we stop. If you're trying to follow along with what was left, let's see, we have Cl minus, we have lithium, and then we have this weird copper species. All of this we're going to not worry about. An interesting point, and your text was written by a synthetic organic chemist, and synthetic organic chemists love looking at patterns in molecular structure and thinking about how they could have made those molecules. This is a particular kind of ketone. It's called an asymmetric ketone because what's on the left is not the same as what's on the right. So in a synthesis problem, if you see an asymmetric ketone, you need to be thinking, I could have made that with a cuprate, because I know a cuprate can deliver one equivalent of a carbanion to an acid chloride without going on to the tertiary alcohol. If you like flashcards, this might be a flashcard reaction to remember to help you, because as I said, the ability for cuprates to stop at the ketone is going to be an issue that you basically have to memorize. Okay, questions? All right, well, so let me show you the other thing that cuprates can do. This, since we've introduced cuprates, it's a decent time to talk about it, but it's going to seem a little bit to come out of left field. And so I'll just summarize it briefly here. Cuprates do what we're going to call conjugate addition, new word, to another new word, alpha-beta unsaturated carbonyl compounds. All right, so first we need to focus in on what alpha-beta unsaturated carbonyl compounds are. Here is a ketone. Here is the carbonyl carbon, and the one adjacent to it, or both of them, we can call the alpha carbon. We do this in OChem. We count, instead of using numbers, we count with Greek letters. So alpha is adjacent to the group of interest. That's the alpha carbon relative to the carbonyl carbon. This would be the beta carbon. And alpha-beta unsaturated would mean that there is a pi bond between alpha and beta carbons, like that. Okay? That is an alpha-beta unsaturated carbonyl compound. You could have any number of things over here, but it would still be alpha-beta unsaturated. Okay, you with me so far? Sometimes these molecules would be called enones, so a ketone that has an alkene at the adjacent carbon, and enone. That's too nasally for my deviated septum, so I prefer alpha-beta unsaturated carbonyl compounds. I'll show you if you want to see, I'll show you the CT scan. It was really interesting. That's a surgery story for another day. So let's talk about reactivity of alpha-beta unsaturated carbonyl compounds. They basically have the same reactivity as ketones, but there's an added feature. So we can draw this resonance structure in which the pi bond between carbon and oxygen is out on the carbonyl oxygen to give you a positive charge on the carbonyl carbon. But now you have another resonance structure with a plus charge adjacent to a pi bond, and you should be able to see based on your 351 organic intuition that I could draw a resonance structure that would look like this, where the positive charge would actually be out on the beta carbon. The lesson from resonance is that alpha-beta unsaturated carbonyl compounds are electron poor or electrophilic at both the carbonyl carbon and the beta carbon. So they have two reactive places. Resonance tells you that. Molecular orbital theory tells you that too. I would love to spend time talking about that, though I think what I will do is simply illustrate that by coming over here to Spartan and drawing an alpha beta unsaturated carbonyl compound, and then showing you, oops, that's not what we wanted. No, where's the undo? Undo, dang it. There we go, downloading it and showing you what the LUMO is for this molecule. Notice for a typical carbonyl, we expect the LUMO to be the pi star on the carbonyl carbon, mostly, with some of it on the carbonyl oxygen. But for this conjugated alpha beta unsaturated carbonyl compound, you can see if you do the calculations, the LUMO is actually out on the beta carbon too. That result may blow your mind, or it may just be, oh, I've seen something like that before. We don't need to delve into it in a lot of detail, but what I want you to realize is that a nucleophile that sees an alpha beta unsaturated carbonyl compound has two spots that that compound can be reactive on. It could attack the beta carbon or the carbonyl carbon. Two different modes of reactivity. If we attack the carbonyl carbon, so if this is our reactive portion of the molecule, nucleophiles that attack here, if the nucleophile attacks here, we get a typical addition reaction. That's sometimes called a 1-2 addition reaction because the nucleophile gets attached here and then a proton usually ends up on the adjacent atom. In contrast, if the nucleophile attacks on the beta carbon, we get something that's called, it's still an addition reaction, but it's called conjugate addition. And it's made possible because the double bond is here, the carbon-carbon pi bond is conjugated to the carbon-oxygen pi bond. So let me give you some examples of 1-2 addition versus conjugate addition. It turns out that organolithiums and Grignard reagents will do regular 1-2 addition, attacking the carbonyl carbon. Cuprates will do conjugate addition. So let's take this same enone starting material and let's have just a generic organolithium reagent. The organolithium reagent is going to deliver the negatively charged R group to the carbonyl carbon. We'll get this tetrahedral intermediate, and then there's no good leaving group, so there we stay until aqueous workup, whereupon the negatively charged oxygen picks up a proton from water, and you get this alcohol product that would be a mixture of enantiomers. We call this a 1-2 addition product because if you start counting from the oxygen, the two things that you added, the R group and the hydrogen, get added to positions 1 and 2. Okay, that's regular addition. That's something that you've seen before. What I'll show you now is the same starting material, and we'll use a generic cuprate, whatever the R group is, followed by aqueous workup. I'll draw the product for you. Here's the new bond that we made, and here's the R group. The R group from the organolithium reagent, oops, that's an eraser, not a, the R group ends up on the beta carbon. This is actually called a 1-4 addition product for reasons that are not immediately obvious and that I probably will have to explain to you next time. But questions so far on these products? Yes?
On the first reaction, is there still supposed to be a double bond?
Yes, thank you for that. On that first reaction, the 1-2 addition product, that should still be there. Thank you. Yeah? When you do the reaction with the cuprate, would you get both enantiomers? The answer is, this is not a stereocenter for this example, but normally, yeah. Okay, see you Wednesday.